Hey everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. We're going to finish up our discussion of redox reactions by talking about reductive dehalogenation of persistent organic pollutants. So as their name implies, persistent organic pollutants are persistent. They're organic compounds that just don't go away very rapidly, and many of them, not all of them, but a lot of them, are chlorinated and brominated and fluorinated compounds. They're halogenated compounds. So reductive dehalogenation could theoretically be a way to get rid of them. And in fact, it turns out that that does work pretty well for a lot of these compounds. So PCBs, of course, they're my favorite chemicals. I love them. I study them. They're what's putting my kids through college. And it does turn out that PCBs can be reductively dechlorinated. So, and PCBs are POPs. They are considered persistent organic pollutants. By the way, the word POPs, doesn't have an exact definition as to what quantifies, what qualifies as a POP. But there is a thing called the Stockholm Convention, which is part of the United Nations Environmental Program. And they have the Stockholm Convention is a treaty under the UN that lists chemicals as persistent organic pollutants, and countries that sign on to this treaty agree to do a lot of things to try to minimize or even eliminate persistent organic pollutants from the environment. So on that convention, there's the original list on this convention. There were 12 chemicals that were listed in the original Stockholm Convention, and those included PCBs and dioxins, which again are chlorinated. And then in subsequent revisions of this list, they have added other things to the list of persistent organic pollutants, including a lot of brominated flame retardants, including a lot of the brominated diphenyl ethers, and some of the perfluoro compounds are now on the Stockholm Convention list. So you could say that POPs are things that are listed as POPs on the Stockholm Convention, but I would argue that there's a lot of other things that are persistent organic pollutants but are not on the Stockholm Convention. So what exactly is a POP is a little bit gray. All right, but PCBs are definitely POPs. They're on the Dirty Dozen original POP list. So PCBs can be dechlorinated by bacteria. They can also be dechlorinated abiotically, but again, as we've discussed previously, most of the useful redox reactions are done by bacteria. Using abiotic reactions generally means that you have to inject chemicals, and it takes a lot of time and effort, whereas bacteria, can be self-sustaining. You could seed a bacterial strain into your waste and let them just go to town. So generally speaking, we try to do microbial reactions whenever we can. So this is an anaerobic process. Again, we've talked about the fact that chemicals are generally designed to be stable under aerobic conditions, but they're not always stable under anaerobic conditions. So under anaerobic conditions, PCBs can be dechlorinated by bacteria. This reduces the toxicity because it removes chlorines, but it doesn't destroy the backbone of the PCB, which means that the PCBs are still PCBs, they just don't have as many chlorines as they used to. And again, we talked about the fact that the more chlorines you have, typically that means you have a more favorable reduction potential. So if you start with a decachloro PCB, that probably has quite a favorable redox potential, and maybe you could easily reduce it down to nonachloro PCB. But the problem is that the decachloro PCB is a giant molecule with a very high log KOW, around 8 or 10, and so it's almost completely sorbed to the sediments and therefore not very bioavailable. So there's always this balancing act. Can you get the thing into solution so that the bacteria can attack it? If it's really, really hydrophobic, it stays on the sediments and doesn't do anything, even though it might have a very favorable redox potential. There's very little thermodynamic data available. There's some computational chemistry studies that have been used to predict redox potentials of PCBs, but that's about it. You can't really measure them because it's too slow and they're just not very favorable. This reaction is regiospecific. So here's the PCB molecule and the numbering scheme. So 2, 3, 4, 5, 6 on the left ring, 2', 3', 4', 5', 6' prime on the right ring. So the 2 and the 6 positions are ortho. The 3 and the 5 positions are meta, and the 4 positions are para. So most Mostly, we see that bacteria can dehalogenate at the meta and para positions, but they leave the ortho position alone. Why? We're not sure. Probably it's a steric thing, but we don't know for sure. So some people have used abiotic reactions. So here's an example. This is an old paper now, 1999, but they used vitamin B12, which is a cobalt-containing porphyrin, to dehalogenate PCBs, and they found that even the ortho positions would be dehalogenated. So abiotic dehalogenation of PCBs can often remove those chlorines that are in the ortho position, but bacteria frequently, but not always, bacteria cannot. So one of my great things that I've done as an environmental scientist, my crowning achievement of my entire career, is that I wrote this great paper where I showed that this microbial dechlorination of PCBs happens in landfills and in sewers and in contaminated groundwater. Previous to my writing this paper in 2010, we knew that PCBs could be dechlorinated in aquatic sediments, but we didn't know that it could happen in these other systems as well. So all of these are anaerobic systems, right? Aquatic sediments are deeply buried, so they don't have any oxygen around. They go anaerobic. Landfills, again, plenty of carbon, plenty of natural reduced carbon to be chewed on, but very little oxygen. So they become deeply methanogenic, and in fact, people harvest methane coming out of landfills as a source of energy. Sewers, same deal. You can get heavy, thick beds of sediment at the bottom of a sewer, and those go deeply anaerobic. Sewers do generate methane. Methane is also called sewer gas. So there you go. So sewers can go deeply anaerobic. That's not a favorable thing. You don't want your sewers to go anaerobic. People try to design their sewers so that they won't go anaerobic, but best laid plans of mice and men often get thwarted and the sewers end up anaerobic. And then groundwater, of course, the same thing. You need a carbon source. If the chlorinated compound is going to serve as your electron acceptor, it would help if you had a carbon source in your groundwater. So if you're at a contaminated site, it's very common that your contaminated site will be contaminated not just with PCBs, but also with PAHs and maybe some fuel oil and stuff. And those could act as a source of carbon and therefore a source of electrons. And then the PCBs could act as your electron acceptor. So these reactions tend to be mediated by a genera or class. I don't know. I'm not a biologist. A group of bacteria called chloroflexi that use the organochlorine compound as their electron acceptors. Many of them are also sulfate reducers. So they can reduce sulfate, and then they can also use these chlorinated compounds. Donna Fennell just published a paper, not even published, it's in review right now, where she identified some bacteria that can dechlorinate PCBs that are not chloroflexi. But much of the genera of bacteria that can do this are in the group called chloroflexi. And again, usually the bacteria can remove the chlorines at the meta and para positions, but not ortho. But there are some situations where they can remove the chlorines at the ortho position as well. So Donna Bedard has been working for General Electric in the Upper Hudson River. General Electric dumped huge amounts of PCBs into the Upper Hudson River, and the bacteria in the Upper Hudson River went to town and started to dechlorinate them like crazy, so that something like 75 to 80% of all the PCBs that were sitting at the bottom of the Hudson River were mono and dichlorinated congeners that were products of dechlorination. Now, the Upper Hudson River got dredged around 2009 to 2015, I think it was. So a lot of that contamination has been removed, but there's still plenty of PCBs in the Upper Hudson River. And the Upper Hudson River has a very strange congener fingerprint because of all this dechlorination that was going on. So what she was saying is that, again, para and metachlorines are the ones that get dechlorinated, and frequently flanked chlorines, meaning that there's another chlorine right next to it on the adjacent carbon. Those chlorines are easier to reduce than the ones that are not flanked. So these are sort of listed in order of favorability, with this being the most favorable, and then going down to unflanked compounds being a little bit less favorable. So, for example, here's some PCBs, 132 and 153. These are common PCBs found in the air chlors, which is the formulations that were produced by Monsanto. And the bacteria come along and they like to remove the flanked chlorines, the ones that have another chlorine next to them. This one's doubly flanked. So they remove those first, and then you get congeners like 51 here and 47, where there's still a bunch of chlorines, but none of them are flanked anymore. And so these can build up as intermediates. And so if you see a lot of 51 and 47, that could be an indication that you have some dechlorination going on. And then maybe it takes another bacterial consortium or different redox conditions or something, but eventually these tetra PCBs, the ones with 4 chlorines here, can get reduced down to these characteristic end products, PCBs 4 and 19. These are dead giveaways. If you see 4 and 19, you know you're looking at a dechlorination signal. So that's, I've been studying this dechlorination of PCBs all over the place. It happens in a lot of different systems, and you can use the congener fingerprint to figure out what's been happening. It turns out that BDEs also get debrominated. So one of the take-home messages from all of these studies of debromination, dechlorination, defluorination of halogenated organic compounds is that you can get this stuff to go in the lab. You know, you put together a little serum bottle, you add your halogenated compound, add some bacteria, give them plenty of nutrients and plenty of carbon, and you will get dehalogenation. The question is, does that happen in the real world, or does that only happen in the lab? So that's one of the reasons why I was really touting my oh so important contribution to the field of science, that I showed that this process was actually happening. Not just that it could theoretically happen, but that it was actually happening in landfills and sewers and contaminated groundwater. And so in a similar fashion, I've noted 2 papers here, and there are more, but 2 papers where we were able to show that BDEs, brominated diphenyl ethers, are being debrominated by bacteria in the real world. Not in theory, not in the lab, but in the real world. I did this in San Francisco Bay sediment. I saw both a microbial debromination signal, and I also saw a photochemical debromination signal. And Eric Christensen and his group did a similar thing in the Great Lakes, where they saw changes in the fingerprints, the patterns of brominated diphenyl ethers in the sediments, and they were able to attribute that to debromination. So brominated diphenyl ethers have this structure, very similar to PCBs, except for they have this extra oxygen in the middle, but they still have, 2, 3, 4, 5, 6 positions, 2', 3', 4', 5', 6'. So they have the same type of congeners as PCBs, and they have the same numbering scheme. So BDE4 is analogous to PCB4. It would be the 2', so 2', dibromo would be BDE4. So you can look at the pattern of BDEs that are formed, and you do get a similar kind of situation where it seems that bacteria can debrominate these things at the meta and para positions, but not as much at the ortho positions. So there's a fair amount of evidence that BDEs can be debrominated in the real world. That's not surprising because the carbon-bromine bond is weaker than the carbon-chlorine bond. So if you can dechlorinate PCBs, you ought to be able to debrominate BDEs. But what's really surprising is that there's some evidence now, and this is a very recent paper from 2019 by our friend Peter Jaffe, who's right down the road at Princeton, and he came here a few weeks ago to talk about this. He actually was able to show that bacteria can defluorinate perfluorooctanoic acid and PFOA and PFOS. And that blew me away. I think a lot of people were really shocked when they saw this paper. But he does have some evidence in the lab that these perfluoro compounds can be defluorinated. Now, whether or not that happens in the real world is a whole different issue. As I said, it's not that difficult to get things to happen in the lab, but whether or not they happen in the real world is really tough to know. But nevertheless, he is seeing some defluorination of these perfluoro compounds in the environment. So redox reactions, really, really important for removing contaminants from the environment, everything from chlorinated methanes and ethanes to chlorinated ethylenes, which are huge groundwater contaminants, and even a lot of persistent organic pollutants. I didn't mention it here, but the chlorinated dioxins and furans, PCDDFs, like what we would call quote-unquote dioxin, that can also be reduced under some conditions. So reductive dechlorination, very, very important process for degrading organic contaminants in the environment. So that's all we're going to say about redox reactions. and we're going to move on to other topics now. I will see you on the other side.